All right, so welcome everybody to today's Quasiworld seminar. So our first speaker is Tianyi Zheng, and she will tell us about uniformly Lipschitz actions on L1 and coarse embeddings. So please.
Thank you for having me here. So some of you might have seen Chris Garland's talk about stochastic embeddings of hyperbolic groups into trees in the Quasiworld seminar. So this talk is a continuation of Chris' talk. So we'll talk about affine actions on L1. So let's just recall some definitions first. So here, let's take a countable group and a real Banach space E. And then an affine action has a linear path, which is a representation of gamma on the Banach space. And then a cocycle path denoted by B here, it satisfies this cocycle identity. And then the most important case is that you assume this pi is an isometry. So this is a classic topic studying groups, how they act by affine isometries on Banach spaces. So when you take the Banach space to be a Hilbert space, then you have this characterization of property T in terms of fixed point. So property T is equivalent to saying that every affine isometric action on a Hilbert space has a fixed point. And then the negation of this is that you find an affine isometric action on Hilbert space with an unbounded orbit. And then the strengthening of that is that you ask for a proper orbit, and that's the Hagerup AT amenability. And you can also consider what happens when you replace Hilbert space by more general Banach spaces. And so this has been studied. So the systematic study of how these fixed point properties of groups acting by affine isometries on Banach spaces was initiated in a paper by Bader-Furman, Gartland and Vergara. So here they define this property FB fixed point for Banach space B. So let me show you a few theorems in that paper. So they considered a lot of different scenarios. So for LP spaces, so they first show that if you have property T, then if you go beneath 2, so you take LP spaces for P between 1 and 2, then you still have this fixed point property. And in L1, when P is equal to 1, because L1 is not uniformly convex, so instead of finding fixed point, you can, the conclusion is that you have bounded orbits instead of fixed point. And then if you go above 2, then things can change. There is an argument due to Fisher and Margulis that you can always go a little bit above 2, but how much you can go depends on the group. So for hyperbolic groups, this P. So if you take a hyperbolic group, it can have Cauchy-Down property T, but it's a result due to Guo Liangyu and later have different proofs that for P sufficiently large, then you will have proper orbits. So what is this? The P is this critical value is the meaningful invariant for the group. So this is a theorem. So these are some results about affine isometric actions. And then you can relax isometry to being uniformly bounded. So this is what we're going to talk about in this talk. Let's relax this isometry pi to a uniformly Lipschitz, uniformly bounded representation. So we say this affine action is a uniformly C Lipschitz if the linear path has norm uniformly bounded by C. And then you can ask the following general question. So suppose you have some Banach space where gamma acts. If you insist on being affine isometric action, then you'll have fixed point or bounded orbits. But if you relax it to this uniformly bounded representation, does the behavior change? Can you find unbounded or even proper orbits? So this is the general question that we want to kind of consider here. And then in this regard, there's a very interesting conjecture for Shalom, which is still wide open. he conjectures that if you take a hyperbolic group, it might have cache-down property T, but it is somewhat fragile if you relax isometric to uniformly Lipschitz, then you will be able to find proper orbits. So it's like you will have this Hagerab AT amenability if you relax isometry to uniformly bounded representations. And this conjecture is wide open. It's only been verified for some Lie group, rank-wide Lie groups for SPN1 by Nishikawa, and then this exceptional Lie group F4 minus 20 by Vergara. And so this is quite a difficult problem. If you think about it, so first you have difficulty producing a cocycle. Right? It's not, if you want to produce a proper orbit, you need a cocycle, and for hyperbolic groups in general, besides the Bussmann cocycle, you do not really have interesting ideas what cocycles to consider. And also you need to put a norm on this space so that it's a Hilbert space, and it's quite a challenging problem. So people considered a further kind of modification of the question. So if we change Hilbert space to L1, do you see a dramatic difference? And here are some recent results, just to briefly review here. Zhu and Mackay, they considered this problem, and they proved that if you take any acylindrically hyperbolic group, then you can find an affine uniformly Lipschitz action with orbits quasi-isometric to the group. So sorry, I'm jumping ahead. So for acylindrically hyperbolic group, they find such an action with the unbounded orbit. And in the special case, when the group is residually finite hyperbolic, then you can have orbit that is quasi-isometric to the group, so completely undistorted orbits into the space. And they in the first statement, they even give this very small bound on the Lipschitz constant, 2 plus epsilon. So in the study of these things, how low you can go in the Lipschitz constant so that you can still have unbounded orbit has some special meaning. It's called the Collins-Hagerup constant. But that's a very refined notion, so let's not go into that. And then in the work of Vergara, he considered actions on subspaces of L1, and he has this result saying if your group can be somewhat embedded into a product of quasi-trees, then using that structure, you can construct some actions. And in a different direction, or say via a different approach, Gartland considered Lipschitz free spaces, and he proved that he didn't need the residually finite assumption. He showed that a hyperbolic group admits a proper uniformly Lipschitz affine action on L1. Also, the orbit has a good compression. You can get 1 minus epsilon compression for the orbit. So I got involved in this because Chris Gartland was at UCSD, and he explained the proof to me. And I thought that you can generalize this to property A. So that's how we started the project. And rather surprisingly, we found some characterizations in connection to notions of coarse geometry. So let me explain the statements. So any questions so far? Is good. So background. Okay. So the first statement is like generally is the kind of builds on the work of Vergara. We show that this conclusion that you can find a uniformly Lipschitz affine action on subspace of L1 with a proper orbit, it's equivalent to that the group coarsely embed into L1. And L1 and L2 are coarsely equivalent, so the statement is the same if it's also the same as it coarsely embeds into Hilbert space. So coarse embedding is a very coarse notion. All you need is a map of your group into the space. So you have a coarse embedding if you can find a map and two control functions. So this lower control function rho minus and the upper control rho plus, and your image, like the distance between fx and fy is controlled by these upper and lower functions in terms of the distance between x and y. And the important thing is that it's like a properties assumption. So here that you have the lower control function has to go to infinity as t goes to infinity. So you kind of manage to put your group into a Banach space, and then the points are kind of, you maintain this properness. And so in this statement, this direction is completely obvious. If you have a proper orbit, you just take it as your coarse embedding. So the content of the theorem is the other direction. So if you assume you have this coarse embedding, and then you can produce a uniformly Lipschitz affine action. So it's like a kind of a non-equivariant embedding, and then you get to some equivariance, not really equivariance, like, uniformly Lipschitz equivalence out of it. So the proof is quite simple. It's I'll explain after a few slides. Okay, and then so I next want to explain a characterization of property A in terms of Lipschitz free space. So that generalizes the theorem of Gartland. You probably have seen before. So this property A was introduced by Guoliang Yu. It's closely related to coarse embeddings. So the story was that if you have a group gamma that can be coarsely embedded into Hilbert space, then you have this important theorem that in that case it satisfies the Novikov conjecture and a lot of other consequences. And then he wanted to give a sufficient condition so that's kind of checkable, and you can prove that the condition is going to imply you admit a coarse embedding into Hilbert space. So that was one motivation. He introduced the property A. And this property is some kind of a non-equivariant amendability condition. So what it says is that so here it works for metric spaces in general. So here I only stated for bounded degree graph. So this amendability condition, it says the following. So you have this graph, and then you give yourself so this epsilon is like the isoperimetry constant. And then it has A if given this epsilon, any epsilon, and then you can find a radius R. And then you're allowed to assign to each point in your graph. So sorry, I think I touched something. I forgot how to move. And then so for this, so the non-equivariance part is that you can take a point X, and then in this radius R, you can assign a probability measure supported on this ball. And so you assign to each point in the graph such a probability measure so that between neighboring vertices, you have this Ritter type condition that the total variation distance, or the L1 distance between this theta x and theta y, is controlled by epsilon. So if you think about the definition of a amendable group, then so it just says that it's like the equivariant version of this. So you take a probability measure supported like with the finite support, and then you translate it everywhere, and then you compare the L1 distance between neighboring vertices. It's small. So the amendable group is somehow you have to use the same probability measure everywhere. But here, property A allows you to choose different assignments at different places. It is a good exercise to check that the free group has a property A. And for groups, it's the same. It has a lot of equivalent characterizations. In one characterization is the exactness of the reduced system algebra, which is kind of important for in operator algebra. And And there are so it's actually very difficult to find groups that does not have property A. It needs to you need to build them. You have to embed some kind of expander type sequence in various ways. So it's really difficult to violate this non-equivariant amenability condition.
So, I mean, you just mentioned this, right? I mean, if you have an amenable group, then of course you get property A, right?
Yeah. So amenable group, of course, it satisfies directly. And if you have and a nice class is that you have a finite asymptotic dimension, then you also have property A.
So what about hyperbolic groups?
They all have property A, yes.
I see.
Yeah, because you can they are it's witnessed by the action on the boundary. They're like topologically amenable. Yeah. So examples of actually it took some effort for people to find examples without a property A. You have these Gromov monster groups that were constructed to weakly contain an expander sequence, and that kind of condition can violate A. And right. And then, so since we're going to state a characterization of property A in terms of the Lipschitz free space, let me remind you the definition of what the space is. So this is a space that it's some space that, this Lipschitz free space was this name. It has many different names. And here call it Lipschitz free space, kind of following this paper of Godfrey and Carlton. So it has many uses. One use is that you can always embed your metric space into its Lipschitz free space just by taking the delta masses. It's like a good isometric embedding. And this this is a space consists of signed measures of a total mass 0. So here you consider this transportation cost in L1. So taking two positive measures on a space, you can take this, consider the transportation cost. So so it goes over all couplings between these two measures, and then you look what is the cost to kind of transport mu into nu. And so in L1, this was called, it's also called the Kantorovich distance or Wasserstein-1 distance, many different names. And then here the Banach space, you can take it to be all these total mass 0 measures. So you have a signed measure, you consider the positive part and the negative part. And then the norm is the transportation cost between the two. So this is called the Lipschitz free space. And the name, one reason for this name is that by the Kantorovich duality, this is a pre-dual of Lipschitz functions. So you pick a point so that to normalize the functions to be 0 at that particular base point. And then this space of signed measures is the pre-dual of the Lipschitz, or this space of Lipschitz functions. So it's a nice Banach space. And so I can state the result. So for this, we don't need to really have take G to be a group. So let's take a bounded degree connected graph. Then it has a property A if you so having property A is equivalent to the statement that you can find a gauge function omega. So by gauge function mean a concave homomorphism. It's like just think of a snowflake or something more aggressive than that. And then you can A is equivalent to the existence of a gauge function omega such that so if you hit the metric by the gauge, then this I think I have a typo here. It's G gamma. So so if you change the graph metric by the gauge, then this metric space has Lipschitz free space isomorphic to L1. So it's let's say this Lipschitz free space is isomorphic to little L1. And then it has a consequence that you when G is a Kelly graph, then your gamma would act on this Lipschitz. So take D to be the graph distance on the Kelly graph, so it's left invariant. Then whatever gauge function you take, this acts by isometry. And then you also have a nice cocycle, which is just take gamma to be, say, you put the delta mass at the point and then minus delta mass at identity. So this is an element in the Lipschitz free space. And then so we have isometric action and a cocycle. And if it is isomorphic to L1, then you get proper action. And sorry, I should say it the other way. So just this part, because your gauge function is a homomorphism, so this is a proper cocycle. And then if the space is isomorphic to L1, then you can transfer this conjugate to L1, and then you get a uniformly Lipschitz affine action on L1 with a proper orbit. So yeah, so you kind of have this natural isometric action, and then if it's by this isomorphism, you kind of go to the uniformly Lipschitz action. Okay. And then so therefore, so just by this, you deduce the corollary that if any finitely generated group with the property A would have satisfy this conclusion that it emits a uniformly Lipschitz affine action on L1 with a proper orbit. So these statements that you have seen before, they actually, these statements, they actually admit characterizations in terms of coarse geometry. So it tells you that L1 is somehow very different from the uniformly convex spaces. For this problem, let me show you this important theorem fixed point theorem when you have a uniformly convex Banach space. So it's like a recent breakthrough works of Oppenheim. So in Oppenheim, he considered SLNR for n at least 3. So you take lattice here. So the most important example is like SLNC for in higher rank. And the fixed point properties of these higher rank lattices, they've been considered for a really long time. And Oppenheim showed that for such lattices in higher rank, any affine uniformly Lipschitz action on a uniformly convex Banach space has a fixed point. So whenever you have uniform convexity, such actions will give you fixed point. And this statement was extended by Tim Delat and Michael de la Salle to all higher rank lattices in simple groups. So yeah, so this was kind of a very important result. And so it tells you, so if you compare the situation with L1, so here all these Lie groups, they have finite asymptotic dimensions. So they all have a property A. So the statement in the previous slides applies to them. So you see the sharp contrast between L1 and uniformly convex Banach spaces. Somehow the geometry of L1 is really strange in some ways, that it allows you to do a lot of things. I still don't quite understand how to really think about it. But in terms of fixed point property, having convexity or not, it really makes all the difference. Okay, so these are the so that's the statement. Any questions? Good. So then I can so the proofs are quite short, so I can basically explain you what goes into these statements. All right, so let's go back to this theorem 1. That so if you the statement is that a group admits so this gamma admits. Oops, I think I shouldn't touch the screen. So gamma admits uniformly Lipschitz affine action on subspace of L1. I want to show that this is a consequence of gamma embeds admits a coarse embedding. So this is a statement. I want to explain how to prove. So it amounts to a subordination argument. It's quite simple. So let's start by taking a coarse embedding. So it comes with control functions. So we have this phi, a coarse embedding into L1, and then this distance is controlled from above and below by the original distance. So this is, and then so we have this is a CND kernel, and then we use I messed up with the order. Yeah, so then we use this theorem of Vergara that he proved in earlier work. So he showed that in order to have a proper uniformly Lipschitz affine action on a subspace of L1, all you need is to find a proper almost invariant CND kernel.
So what is a CND kernel?
It's by def. Oh, I think I messed up with the. If I can find no. This CND stands for conditionally negative definite. I think so I somehow messed up the order. So it's a conditionally. So you look at this kernel. Say let's call it the phi xy, and then you take you take these. So you consider if you take a finite, so you take a finitely many points x1 to xn, and then make this n by n matrices, and then you look at so you think of it as a quadratic form, and only consider it vectors that has the total sum has the summation 0. So the vector entries sum up to 0, and then you want it to be negative definite on that subspace. So it's called conditional because you'd only consider like such vectors, and then you can so they come from these kind of matrix coefficients that if you take an embedding into a Hilbert space, then this norm squared is a CND kernel, and if you embed into LP, then this then you can take the LP norm and then to the power P. So these are all CMD kernels. So you can check quite, yeah. And then there's this classical theorem of Schoenberg saying that CND being a kernel being CND is equivalent to that if you take this e to the negative lambda times p, this kind of Laplace transform like thing, then you get positive definite kernels. So these are really equivalent. And the good thing about CND kernels is that you can subordinate them. So if you take a Bernstein function and compose it with the CND kernel, then it's still a CND. So Bernstein function is you can consider take the definition to be that they admit this Levy-Khinchin representation that you have a constant and a linear path, and then the important thing is that you that it looks like a Laplace transform of a measure. And here the measure need to satisfy this mild condition that near 0, it needs to be integrable with this, with x. And so this is like a characterization of Bernstein function, and you can kind of by definitions check that if you compose a CND kernel with a function, then with a Bernstein function, then it's still CND. So now, so if you come here to Vergara theorem, so if you have some CND kernel, if you find a Bernstein function to compose it to be almost invariant, then we find proper, we can use that to find a proper uniformly Lipschitz affine action. So that's how the proof of the first theorem goes. Right, so almost invariant means, so if it's isometry, then we would have C equals to 1 here. So if you have this CND kernel, you move it around by the group element, it remains the same. So that's the same as saying that it comes from an isometry. But here we want a uniformly bounded representation. So we only need this kind of almost invariance. And now if we start with the coarse embedding, so it comes with the upper and lower control functions. So if we find a Bernstein function to compose it to be almost invariant, then we're actually done. And this is can be done easily by quite easily by a rescaling trick. So we take the control functions and then apply the following rescaling lemma. So if we have some non-decreasing function, then you can always find a gauge, meaning a non-decreasing concave homomorphism, so that if you compose them, then it becomes somehow this almost invariant. So this effect of rho becomes a fixed multiplicative constant on the right-hand side. So this is completely elementary. You can just choose omega according to rho. You just go to the look at when it doubles, and then you take omega to scale it back. So it's really purely a scaling trick. And then with a bit more care, you can choose this omega to be a Bernstein function. So you see the shape of a Bernstein function is that it looks like a Laplace transform of a measure. So you just do it more carefully with choosing the measure, like so that this scaling, you can write it as this kind of a transform, and it's also an elementary operation. So this way, it allows you to do this subordination to turn the control functions into a multiplicative constant, and that's basically the proof of the first theorem. It's somehow this Vergara theorem tells you all you need is a CND function that's a kernel that is almost invariant, which is not true at all in other spaces. If you try to think about what happens in Hilbert spaces, there's no such theorems. It's very like having this kind of almost invariant CND kernel is very far from actually you can build a affine as almost invariant action. Okay, so that's the first theorem. It comes from this scaling. And then, so next in remaining time, want to explain the property A characterization. So like amenability, there are dozens of equivalent characterizations of property A, and Gabor Alek had done a lot of work around this. So this theorem, you can find in this nice paper of Alek and Tima. They called it the long cycle theorem, and they give you the whole proof for these equivalent characterizations. So here, I'm not going to explain all the definitions. So we're going to use that property A is equivalent to what's called the strong hyperfiniteness. I'm going to show you the definition on the next slide. So it agrees with this kind of, people understand amenability is closely related to hyperfiniteness. And so here is this formulation called strong hyperfiniteness that's equivalent to property A. So, so the definition is in terms of random partitions. So if let's do it in the think of X graph, a bounded degree graph, and then so we say a subset is a K separator if so you have this say my graph is just a Z square, and then I can take a separator to be something like these lines, and then you keep going. And so such a subset is called a K separator if if you remove the set, then you have finite connected components. And the K here is a quantifier that you want all these components to be to have size at most K. So that's the notion of a K separator. And then we say that this is strongly hyperfinite if you can find a probability measure P on the set of K separators. So you want to pick a random K separator, and then so that for any point in the space or any vertex, the chance that you are on the separator is less than epsilon. So it's like a random partition, and then the probability that you fall on the separator is bounded by epsilon. Okay, so Alec proved that if you have a bounded degree graph G, then it has use property A if and only if it is strongly hyperfinite. So this amenability condition and hyperfiniteness condition, they're really equivalent. So we're going to use this formulation. So you can compare it to this notion of separation modulus in the study of random partitions. So this notion is quite important in various problems like Lipschitz extension and things like that. So let's just take a look at this definition and compare it to hyperfiniteness, strong hyperfiniteness. So we say that this space has a finite separation modulus. So this is a constant sigma. If you can find a probability measure P on the set of K separators, and then quantitatively you want, so here is it's the same as asking the, I guess the draw it's not so nice. So here the formulation is that you take x and y, and then you look at such an edge. So dxy is equal to 1 in that case. And you want the probability that they fall in different components to be less than sigma over k. So this is like a quantitative strengthening of the condition before. So to be strongly hyperfinite, you just want a uniform choice of k such that you have a random k separator. The chance that you fall on the separator is bounded by epsilon. And now you, in this separation modulus, you wanted this probability to be a sigma over k. So it's like a stronger version of quantitative version of the previous notion. And then if you compare the two definitions, then you see that if you allow yourself to change your graph metric by a gauge function, then you can arrange for such conditions to hold. So if you have a graph that has that is strongly hyperfinite, then by this rescaling trick, you can hit the graph metric by the gauge so that it has a finite separation modulus with respect to omega composed with d. It's the same kind of a scaling trick as before. So that's the connection between the two. And then, so under this finite separation modulus, have this, people have studied properties of such spaces in terms of stochastic embeddings into trees. So, this lemma I learned from Chris. He mentioned that it goes back to the work of Bartel back in the 90s. So there is within computer science literature that people want to study kind of how probabilistic approximations of metric spaces, especially how you can approximate more complicated spaces by trees in some sense. And the lemma says that if you have a finite pointed metric space with a finite separation modulus sigma, then you can find a finite pointed ultrametric space and a weak stochastic embedding of this finite space into U. And the distortion is controlled by the separation modulus. So that was lemma to Bartel, and it admits many different versions, and people rediscover this lemma a few times later. And here, just to remind you what stochastic embedding is. So you consider a probability distribution on maps from one space to another. So you want to kind of consider a random map. And then we say that a random map is a stochastic embedding of distortion D. If so, it's a kind of a strange formulation at the first glance. So instead of asking it to be Lipschitz, you ask it to be non-contractive. So you want a lower bound first to guarantee that all points are separated at least according to their original distance. And then you will make your below up. You might blow up the upper bound, but the second condition insists that on expectation it's Lipschitz in expectation with the distortion D here. And then the weak version just considers the probability that you go too far in the embedding. So you consider the tail probability. And then if we say that it is a weak stochastic embedding with distortion D, if this is controlled by this weak L1 norm. Okay, so the weak one is actually easier to work with because it considers kind of one scale at a time, and then the stronger version will ask you to kind of integrate over all scales. So Bartel's lemma tells you that let's go back to the lemma. It tells you that if you have a space with a finite separation modulus sigma, then you can do an embedding into like a tree-like space with distortion, weak stochastic embedding with the distortion controlled by the separation modulus. So it's a kind of a useful approximation. And so in the earlier work of Chris, he showed that you probably have seen this theorem in his talks before. So he showed that if you take a compact finite Nagata dimension metric space, then you can snowflake the metric, and it stochastically embeds into an ultrametric space. So here, if you don't snowflake the metric, then you get a weak stochastic embeddings like in Bartel's lemma, and then any snowflake will turn it into a stochastic embedding. And then he showed also that if you admit a stochastic embedding into ultrametric space, then the Lipschitz free space is isomorphic to L1. So that's where the kind of, if you want to conclude the Lipschitz free space is isomorphic to L1, a sufficient thing to do is to stochastically embed it into a ultrametric space. And he used this to prove his theorem on Gromov hyperbolic groups. And so the same kind of proof scheme can be carried over to property A case with this scaling trick, essentially. So that's the sketch of the proof. So we have we assume strong hyperfiniteness. So we have this, you have this distribution on K separators so that the chance you fall on the separator is controlled. And then using this rescaling trick again, we can show that it gives you that if you rescale the metric, you can get this G equipped with omega composed with D that admits a finite separation modulus. And then with the Bartel's lemma, you can weakly stochastic embed it into ultrametric space and then apply Gartland's results. We get this Lipschitz free space is isomorphic to L1. So this is like a generalization of what happens in the hyperbolic case. And then in the converse direction, so the interesting thing is that this admits a converse. So that's the last bit of the proof. So this is the if and only if. So if in the other direction, if we now have a graph without a property A, then we want to show that you cannot rescale the metric so that the Lipschitz free space becomes isomorphic to L1. And here we use this characterization of uniform local amenability. So it's also equivalent to A. So if you do not have A, then it means that you can find a local expansion in your graph So the statement is that if you fix any size k, then you can find a finite subset in the space such that all subsets inside L of size at most k has C expansion. So it's like you have a lower bound for the expansion constant, but up to certain size, not to the whole set. So it's like you have this finite. You can find a sequence of finite sets in the graph, such that they admit bigger and bigger local expansion, but they're not expanders themselves. You only have a local expansion. And then, so for this case, if we want to extract some Poincare inequalities, so we do not have kind of expansion all the way in these local regions like in expanders. So what we found were these, we can find these Poincare inequalities for some point processes. So here I want to consider Poincare inequalities of this form. So if you take just for notation, if we have a finite set X, then UX denotes the uniform measure on this set. And then, so here V is a finite set. So you take this region with a local expansion, and we call the vertex set V. And then here we consider some random subset. Say this is my set pi. It has some distribution. And then I consider the transportation cost from uniform measure on this subset to the uniform measure on this vertex set. And then, so this is like a L1 Poincare inequality. On the right-hand side, you have the usual like a Dirichlet form, like this. The right-hand side is the same as what you would see in expander inequalities. It's you take a function and then look at the average kind of Lipschitz norm. And then the left-hand side is the average kind of, you look at an instance of this sample and the uniform measure and look at the pairing between this difference and the same function f as the right-hand side. So this is, if you take a good example is, so if you take gamma to be a singleton set and X is a uniform in this V, then having this Poincare is the same as saying this graph is an expander with Poincare constant C. So now in the case when we have a graph without property A, then we only have a local expansion, not like a full expanders. So so what we found is this shape of Poincare inequality. So we are able to find a sequence of finite regions in the graph, and then percolation parameters pk going down to 0 to have a more and more sparse sets, such that so the regions gets bigger and bigger, and this percolation constant goes down to 0. And then we do independent Bernoulli percolation in this region with the pk constant. And then this transportation cost between this pi k and then the uniform measure on this region is satisfy this shape of Poincare inequality. And then this is enough to prove the converse direction that you cannot find a rescaling of the metric. Yeah, so it's kind of the usual situation where if you want to find abstractions for embedding into L1, then often you need to find like the suitable Poincare inequalities to witness that. And here, this kind of uniform measures sparse percolation points, it captures the local expansion in the right way for the converse direction.
Oops, what happened? Hello?
Yeah, I cannot hear Tianyi.
Can you hear us? Your video froze.
I mean, it looks like there is some connection problem there, so we should just wait for the.
Okay.
Yeah, you dropped for a second here.
I think I will just disconnect it for a second. Should I
Yeah, I have to make you co-host again, I guess. Sorry. No, you should be co-host.
yeah, maybe, but I can share the.
Yeah.
I think I have a. Yeah, let's stop here. Okay. I don't know when I lost the connection, but that's the end of the my
Oh, I
slide.
see. So, all right, fair enough. Okay, so then let's thank Tianyi for a very interesting talk. Let me start the discussion. So, any questions or comments? Well, let me ask you one thing. So, how are there any mechanisms to somehow promote a uniformly Lipschitz action to something that is isometric? How far are these two things removed from each other?
They can be very fast because from these fixed point theorems, you can see if you have a group with a property T, then this theorem from Bader-Furman, Gelander-Renaud already tells you that any affine isometric action on L1 will have bounded orbits. But once you relax that, you can have like a quasi-isometric orbits. So it shows you if you relax one to say 2 plus epsilon, then you can kind of do a lot in it's isometric and somehow uniformly bounded representations. They behave very differently.
Yeah, I see. Thanks. So, other comments or questions?
Yeah. Wanted to know what are the examples of groups without property
They have these people construct them on purpose, like you make an effort to produce them. They have the Gromov monster groups that they weakly contain expanders. They do not even coarsely embedding to L1. And then there is another way of constructing such monsters due to Damien Osaja that he could, yeah, there are different methods to in some sense include expander sequence into your group. So yeah, there are very few examples without property A, and yeah. At first, people hope that all groups will have that property, then you solve the Novikov conjecture and all these great consequences to Guoliang work. But then you do have these strange ones.
Okay.
Other comments or questions?
I don't know, like, is Shalom's conjecture sort of the main motivation for sort of this sort of questions, or like sort of like why, sort of what are other sort of interesting connections there that kind of people look at sort of?
One thing was motivated by these fixed point theorems that for higher rank lattices on uniformly convex Banach spaces, you can relax the isometric to uniformly bounded, still have the same conclusion. And then people want to understand like what is the real difference between like in what scenarios having these two behave the same or differently, how different is that's the main motivation to understand the contrast between isometric and uniformly bounded. There was some research about this Hagraf-Collis constants, which I do not really understand. It goes too far into operator algebra. Yeah, but people have been looking at uniformly bounded representations and the related affine actions for a long time.